In this video, we are going to learn about the design of an arithmetic logic unit. So as the term indicates, it consists of arithmetic as well as a logic unit. So we will be learning about the function of arithmetic logic unit, and then we will be focusing on first how to design the logic design of an arithmetic unit, and then the logic design of a logical unit which performs the logical operations alone. Arithmetic unit means arithmetic operations alone. And then what we are doing is we are combining all these operations to a single module in such a way that we are performing some changes in the arithmetic unit so that it performs the functions of all the logic operations also. Okay, so what is an arithmetic logic unit? It performs both the arithmetic as well as logic operations. So now we are going to learn about the design. We are going to design some arithmetic unit, and the logic unit also we are going to design. So for that we need to know some basic things. So arithmetic ALU means that it is a multi-operation combinational logic design digital function. It performs a set of basic arithmetic and logic operation. Selection lines, it helps in selecting a particular operation in the unit. K selection variables, it can specify up to 2 raised to k distinct operations. So here we are having some selection lines like S2, S1, S0. Based on these selection lines, it will be able to select the different operations that will be performed in the ALU. And A and B, they are the inputs that is fed to the ALU. We will be having a carry in and carry out. And based on the input, this diagram, it shows the 4-bit ALU in which it receives 4 bits from each operands, and the output also it will be in the form of 4-bit. Okay, so S0 to S2, it helps in performing the different operations. So based on the number of selection variables, k selection variables, it determines the k distinct operations. Among these selection variables, S2 will be used to select the mode, whether it is to perform the arithmetic operation or to perform the logic operations. For that purpose, it makes use of this S2. And S1, S0, it helps in determining the different operations belonging to individual, that is the arithmetic or logic operations. So S1 and S0 is like a function select, S2 is mode select. So first we are going to learn about the design of an arithmetic circuit. So the basic component of arithmetic circuit of any ALU is a parallel adder. So a parallel adder, it is constructed with a number of full adder circuits that is connected in cascade form. So by controlling the data inputs into the parallel adder, it is possible to obtain the different forms of arithmetic operations. So here we can see some figures, that is we are making use of the parallel adder which takes inputs A and B. If carry in is equal to 0, then the operation performed will be like A plus B. If carry in is equal to 1, the operation performed will be A plus B plus 1. Okay, now considering this B input, if the input given is B complement and carry in is equal to 0 means the output will be F is equal to A plus B complement. And if carry in is equal to 1, then A plus B complement plus 1. And this operation, it performs what? The subtraction. Okay. And next is like if the second operand it is 0 and carry in also if it is equal to 0 means what is the output? it is equal to A. That is just it transfers the value of A. And if the carry in same case, if the carry in is equal to 1, then it will be incrementing the value by 1. And next case is like a parallel adder which takes all that is the second operand. If all the values they are all the bit informations, if all is 1, then it performs the decrement operation if the carry in value is equal to 0. And second operand, if all is 1 and the carry in is equal to 1, then again it performs the transfer operation. So this we can see with the help of an example. That is, if A is taken as some value 9 and its binary equivalent will be 1001. Okay, 1001. And 2 raised to n, if n value is taken as 8, if n is equal to 8, then 2 raised to n will be equal to 256. So the binary equivalent will be like 1 followed with n zeros. And if 2 raised to n minus 1 if it is taken, then what happens? You will be having n ones. That is all ones you will be having. Then a plus 2 raised to n minus 1 if it is taken, what it happens? A plus 2 raised to n minus 1 if it is taken means you will be getting the value as combining these two, a and 2 raised to n minus 1, you will be getting this result which is equivalent to 256 plus 8. So the equation what you are getting is, if it is written like 2 raised to n minus 2 raised to n plus a minus 1 is equal to some value you are getting. Okay. Now if you are removing that is, this can be treated as an output carry. So if I am removing this output carry, what you will be getting? You will be getting the value as a minus 1, which that is when you are subtracting the a value, when you are performing the addition of a with this all ones. Okay, adding this a content with all ones, you will be able to decrement the value by 1. So how it is being done, it is explained in this example. Okay, you will be getting the result like this. From this result, if you remove this as an output carry, you will be getting the value as a minus 1. That is the operation that is performed over here, decrementing the value of a by 1. Now, so input carry in goes to the full adder circuit in the least significant bit position, and output carry C out comes from the full adder circuit in the most significant position. So when you see here, C in and C out is there. C in will be coming in the least significant bit, that is, it will be given as an input to the adder, and the C out will be coming as an output from the adder through the most significant bit. C out comes from the most significant bit. C in comes into the adder in the least significant bit. Okay. Now what you are going to learn is about the input B. So we have learned about C in, C out. Next is about the input B. So input B is applied in 4 different forms by using the following circuit. So this circuit name is true complement or 1-0 circuit. True complement or 1-0 circuit. So this circuit will be used as an input to the full adder. So how it is being done? That is, this is being chosen based on the function that is, so this can be treated as a function table. And from this function table, you will be able to generate the Boolean function. From this function table, you will be able to generate the Boolean function using the K-map that you have learned in the previous semesters. So if you are considering here like S0, S1, 0 and 1. 0, 1. So here you are going to determine the output of this y. Okay. So 0, 0 means y is 0. 0, 1 means it is bi, b1 complement, and 1, 0, b1, and 1, 1 is again 1. So from this you will be able to generate the function, isn't it? Boolean function you will be able to generate from this with the help of K-map. So, so what is the function that will be generated? S1, S1 B1 complement, S1 B1 complement plus S0 B1. S0 B1. Okay, this is the Boolean function that will be generated by making use of the K-map method. So this function based on this function you need to draw the circuit. So here plus is there, so an OR gate will be used. Then two terms are there, so which makes use of the AND gate. So two AND gates will be used, and one AND gate will be taking the input S0 and B1. So S0 and B1 will be given as an input to one AND gate, and the other AND gate it will be having S1 and B1 complement. So in order to get the B1 complement, it will be fed as an input to a NOT gate and then to the AND gate, and S1 also will be passed to the AND gate. So the output of that will be fed, both output of both the AND gates will be fed as an input to the OR gate to get the output Y. Okay, so this is how an input B will be implemented. And input A, in case of input A, it is directly applied to the parallel adder, and the input B is being modified for all the arithmetic circuits that is being shown here. Okay, so based on this, we are going to we will be drawing this full adder, that is a full adder circuit that is performing the arithmetic operations. So this much things, this will be the B circuit that we have learned earlier. A is directly given as input to Xi, B is given as an input to Yi. We will be having a Cin that is given as C1, and in addition to that we need to take S1 and 0. In previous case we have, here also we have made use of this S0 and S1. Similarly here also we need to make use of this S0 and S1, which will be given as input to the AND gate, these AND gates. Okay, these two AND gates, it will be given as input to those AND gates. Okay, so since it is a 4-bit, we need to have 4 full adder circuits here. Previously only one B input was shown.